This problem is probably the hardest I've ever attempted to solve. I'm not even kidding. I think this is honestly not elite code hard. I think this is a different class of problems. I think super hard. I've never done code forces, but I assume that this is kind of the caliber of problems you see on code forces. Hopefully, I think you at least learned like how I kind of approach problems. This one, I will admit, was too hard for me. And the reason I don't feel bad about it. So I was reading this AMA on code forces from Scott Wu. I recently made a video about him if you don't know who he is. He's basically a competitive programmer, really, really good. One of the best of all time. He's also more widely known for creating Devin, the AI software engineer. But we're not talking about that today. I thought this response from him was pretty interesting as it relates to getting good at competitive programming, which is very similar to, getting good at Leetcode. At least, Leetcode is easier than competitive programming. Let me just say that. I'm not a competitive programmer. Hey Scott, what's the appropriate amount of time one should spend on some problem before giving up on doing it at all by themselves and look at the tutorial instead? Some people say 15 to 20 minutes max, some people say a long time, but his response was really interesting to me and even kind of surprising. This is an interesting one. It seems like a lot of people recommend waiting and thinking more, but personally, I look at editorials as soon as I get stuck. The key piece though is to make sure to connect the motivation of the solution. How could I make the insight that leads to discovering the solution is a separate question from what is the solution. And it's important to think about the former as well. So what he's saying is understanding the solution, like sliding window, backtracking, DFS, whatever. Knowing the algorithm is good. That's necessary. It's important. You have to do it. But it's easier than understanding why. When I make videos, that's what I try to do. Of course, I show you the code. It runs usually, but I try to explain why. You probably know that. The first part of what he says, he doesn't spend a lot of time thinking about it. That was really interesting to me because when I started Leetcode, I would spend like 5 hours on one problem. I just thought that's the only way to learn. But no, even this guy's a genius. If you watch that other video, this guy is a literal prodigy. He doesn't even waste his time. He's not even like, I'm not going to spend a few hours on this. Maybe he wouldn't be able to figure it out. Some problems are pretty damn insane, right? There are some geniuses out there. It took them weeks, months to come up with certain algorithms. Why would he want to rediscover that? Why would he want to reinvent the wheel when that's not his priority? He's not trying to invent new algorithms. He's trying to get good at competitive programming. So when you're trying to get good at Leetcode, there's no shame in looking at a solution. Okay, you didn't derive, the shortest path algorithm by yourself. Don't feel bad about that. Look at the solution. Okay, fine, but understand it. Knowing all of that, I think it'd be kind of interesting if I showed you how I approach a new problem that I probably won't be able to solve. Let's do it. So let's go to Leetcode, up the difficulty. Let's go to some of these hard problems, sort them based on difficulty. So let's try this one, minimum reverse operations, because it's a relatively recent problem, 2600. I guess I could try that one as well. And lucky for us, this problem doesn't even have an editorial. Let's see what's going to happen. Minimum reverse operations, we're given an integer n, integer p in the range 0 to n minus 1, representing 0 indexed array of length n. Okay, n is that. This is some live problem solving that you're seeing from me. All positions are set to zeros, except position p, which is set to 1. Okay, so a binary array. Interesting. I'm kind of just looking at the example. Okay, looks like this is different than what they are talking about, so we're going to need some more context. I guess n and p are representing arrays. They're not necessarily arrays, which is funny. Why do they even give us this if there's no parameter? So this is me getting mad because Leetcode problem descriptions are really annoying. Okay. Given an integer array band containing some positions from the array, the ith position in band array of the ith position is equal to 0 and band of I is not equal to p. So what this is basically telling us that every value in band is not going to be equal to p, because if it was equal to p, we know that p tells us the index where the value is set to 1. So this is just an overcomplicated way. So that's hard problems for you, really overcomplicated descriptions. You can perform multiple operations on the array. In an operation, you can choose a subarray with size k and reverse the subarray. However, the 1 in array should never go to any of the positions in band. Now, I'm getting to the point where I realize that me talking to you guys as I'm explaining this is making it harder for me, because if I had read this part before trying to understand this, I would have gone faster. So this is a little bit of the thought process, because now we realize that band just tells us every position in the input array that the 1 is not allowed to be at. And initially, we know 1 will not be at any of those band positions. positions. Return an array answer where for each I in the range, answer for I is the minimum. Okay, so at this point, I know that the result is going to be of size n, so let's just initialize an array like this. This way, it's kind of like us taking notes here. And then we know this is what we're going to return. At least we have a little bit of the starter code set up. This is the minimum number of reverse operations needed to bring 1 to position I in the array, or -1 if it's impossible. We know for when it's impossible, I'm just going to do what I know so far. But in some cases, like in a real coding interview, I probably wouldn't start coding immediately, though I don't think this is bad. I mean, this isn't real code. This is just this is the same as taking comments, for example. But now I know band tells us the impossible positions. So I'm going to go through for B in band. I'm going to say result at B is going to be equal to -1. This tells us this position can never have a proper result. A subarray is continuous, blah, blah, the values of answer of I are independent for all I's. The reverse of an array is an array containing the values in reverse order. Okay, I don't even know why I read that. Okay, so now examples matter. I don't even know half of what this problem is even asking yet to this point. Just quickly reading the constraints, nothing special. I assume band is going to be smaller than n. Okay, they do confirm that here. It's going to be less than or equal to n-1. And of course, they're all going to be in bounds. Okay, so we don't worry about any of these crazy things. Let's look at an example now. This is where I start to whiteboard or start to do comments. So to make this easier for you guys to understand visually, let me try to draw it out. I remember the problem description, so I'm not gonna focus on that. I'm gonna focus on the example. So we know size array of size 4. P is the position where the 1 is. So we have this binary array, and we have an array band. I'm not gonna draw that out. It's already there for us. We know we have an array result. I'm going to draw that, I guess, over here because I want these to match up visually so it makes it easier for us to understand. We initially fill them all with zeros, right? But I know immediately that the band positions are going to be -1. So 1, this position is going to be -1. This is going to be -1. Okay, I'm not even thinking about code. I'm not writing code, right? You don't see me writing any code. I'm just drawing. I'm just thinking about it. So how many reverse operations is it going to take to bring 1 in this spot? It's impossible. How many in this spot? It's impossible. How many in this spot and this spot? That's what we're trying to answer so far. We're just drawing it out. Here, 1's already there. How many operations does that take? That's 0, right? Well, what about over here? We can take any one subarray and reverse it such that we bring 1 here. So now I'm starting to notice a pattern. I haven't coded it up. I'm asking a question in my head. I'm asking myself, is it always gonna be possible to bring 1 in every position, assuming it's not a band position, right? Band positions are easy. We don't worry about those. And the starting position is also easy. So now I'm wondering, is it always going to be possible for me to bring a value in every single position? Intuitively, I think probably not, because that's the whole motivation of having band positions in the first place. Let's try some examples now. Obviously, for us to bring 1 in this position, we would just choose the entire array, then reverse it. If we do that, 1 is going to end up over here, which is valid. So that's 1 operation. Now, when you think about this subarray that we defined, I'm still trying to, in my head, answer the internal question of, can we always bring a 1 in every open spot? When I chose this subarray, I really chose it by picking the endpoints, right? That's what defines a subarray. We don't always have to pick 1 as the endpoint, right? 1 could technically have been over here. And had we reversed this array, we would have ended up moving this 1 over here, right? But now I'm asking myself, why would we ever do that? Why would we ever pick an array bigger than that? Are we always going to pick 1 as the endpoint? Because we could have accomplished the same thing here by picking these 2 endpoints. So now I'm honestly not sure. This problem seems easier than it should be. Or should we always pick the 1? Now I'm starting to think maybe there's some counter example I can think of. But at this point, let's assume that we're always going to pick 1 as one of the endpoints. And then if we want to put 1 over here, let's just pick that as the endpoint. Is there anything wrong with this approach? So far, I'm not able to think of it. Is it really this simple? I guess that's what I'm asking myself. Is it always going to be 1 for all these open spots? This seems too easy. I must be missing something now. Okay, and now I realized I didn't even read the entire problem. If you read this explanation, k is equal to 4. We can only pick subarrays of size k. Okay, that's dumb by me, right? So now you can see reading the problem is pretty damn important. That's usually where a lot of mistakes come from. Okay, so now in this case, the original solution still works. It's 1 in this case because k is equal to 4. This is the subarray that we pick. But now I can think that in some cases, let's say if k was equal to 2, we're just going through some examples. We'd pick these two endpoints. Let's still assume that we always pick 1 as one of the endpoints, though I can think of a counterexample where that might not happen. So now I'm starting to realize this problem is kind of a, politically incorrect term. This is kind of a crackhead problem, because in this case, if we try with k equals 2, I'll show you what I mean. If we now pick, this subarray, we can't do that. We're not allowed to do that. Therefore, 1 can probably never end up here. So now I'm thinking, can we be greedy? And I already thought in my head, probably we can't be greedy, actually. Probably we can't, because when I'm being greedy, I'm always picking this one as the endpoint, because if k is equal to 2, okay, we'll just push it as far as we possibly can, right? It's kind of like the problem jump game. Jump this guy as far as he can. Well, what if he lands somewhere where he's not allowed to land? So that's a problem here, right? But think about this. Think about this example where this is actually a 0, right? Where this is not a banned position. This is not banned. And let's say k is equal to 3. Well, we can't do this. This is a subarray of size 3. We can't make that jump because it's still invalid. So we kind of have to jump here first, but we're not allowed to do that right now because this is a subarray of size 2. But what if we had an extra element? Consider this was the original example. Well, here we can pick this subarray. This is a subarray where 1 is not at one of the endpoints, but actually, even if we reverse this, it's not going to do anything for us. So it looks like I created the wrong example. So the point I'm getting at, there is an example where sometimes we're not going to be able to be greedy. I don't want to spend a lot of time drawing it out, but you can probably think of one. But so at this point, I've realized that we can't be greedy. We can't always consider that as the endpoint of the subarray. So at this point, I've learned a lot about the problem. There's still a lot I kind of need to learn. There's some patterns I still need to recognize, but I don't want to waste too much time on this. So I'm going to keep going for a little bit until I feel like I'm really, really stuck. Then I'll update you guys on how far I got. And then we're going to go look at the solution if we can't figure it out, and then see how we can actually understand the solution and understand why it works. Because I spent a few minutes. It's important to try to solve a problem until you really get stuck. And that's when you look at a solution and then see, well, where did I go wrong originally? Okay, so it's been like 10 to 15 minutes and I've gotten to the point where I've realized this is a really hard problem. I might not be able to figure it out. And even if I can, it's going to take me a really long time. So we're going to look at the solution. I'll quickly summarize what I know about the problem so far. Looking at a slightly different example than this one, let's say we had 1 here, and let's say we have 3 zeros before and after. Let's say k is still equal to 4. What I've kind of realized is that basically depends how we pick the window. We have 4 choices because in a window of size 4, we can put 1 here, or we can put it here, or we can put it here, or we can put it here. Now, when we do this reversal, we might be moving 1 to the left by 3, right? By 3 here, or we might be moving it to the right by 3, and it's going to go both ways. But let me just kind of show you here. So this window, we'll move it to the right by 3. This window, we might move it to the right by 1. This window, we move it to the left by 1, and here, we move it to the left by 3. So basically, in terms of like our choices that we have, we can either do a +1 in terms of like the position that we change this from. We can do a +3, we can do a -1 and a -3. So that's going to be different depending on the position of 1. Like here, we can't really do a minus. That's because there aren't any positions over there, but we can do +3 here. We can't do a +1 though, because that would require elements over here. So that's kind of why I'm getting to the point where this might be the wrong line of thinking, because this is so damn complicated, right? That's kind of why I'm getting to the point where like, I kind of want to just look at the solution now because I'm going possibly down the wrong track. Now, if this was known to us, if we could somehow figure out how we're allowed to move, then it does seem very similar to jump game in that to fill in positions, we could approach it like, okay, let's try to figure out how many moves it would take us to get here, right? And then run some algorithm or some loop and then try to figure it out for every single position like that. Or we could think about it another way. Like from here, we could do some kind of traversal, right? Traversing this array, we could say, okay, I'm allowed to move a +1, or I'm allowed to move +1, +3, -1, -3, like from here, right? Like I can do this, or I can do this, and this. And so even though +2 or -2 wasn't included in this set, if I do a +1 and then I do from here, if I do a +1 here as well, and from here I do a +1, it looks like we're allowed to reach every single spot. So the only thing is we're counting, right? So for here, it's 1, here it's 1, here it's 2, here it's 1, here it's 2, and here it's 1. So now I'm kind of getting to the point where this is kind of a traversal. Potentially it could be a graph traversal. So to me, it looks like possibly backtracking, though given that we're looking for the shortest path meaning minimum number of jumps it takes to get to each, graph wise that sounds like breadth first search. But even then I would need this set, and even if I knew it, actually this does seem possible because the breadth first search is gonna continue like this, and the only thing is if we land on these, I guess we stop the breadth first search, like we're not allowed to visit these positions. And I think other than that it's fine, but figuring this out is not straightforward. Like that's gonna be kind of annoying, though it does seem possible. But again, like I could be on the wrong track. I don't want to write a bunch of code and then I'm missing like one edge case. Time to look at the solution. So there's no editorial, so let's look at these solutions. Just so you guys know, back in my day, there weren't a bunch of helpful YouTube videos about problems. Like the only way to learn was to look at some of these really cryptic solutions. So there's a Python one, thankfully. Let's take a look at it. Thank God there is at least some explanation. Let's try to understand it. It looks like it is a graph problem to some extent. Sorted list. So I have no idea how sorting is relevant to this problem. I was not able to make that conclusion. So let's try to figure out how. And I'm probably going to do a lot of silent thinking right now, and then I'll try to kind of explain why the solution works and try to give you my interpretation of this discussion solution. We start our investigation. If there is a 1 at position node, what neighboring nodes could it reach in one move? Kind of along like a greedy train of thought. I left, before reading this, let's just see what he's saying. B, the starting positions of the subarray to be reversed. Okay, that makes sense. I think he's talking kind of about what I was, like how we can position P in any one of those 4 slots, right? So this is I left is going to be the starting position minus K plus 1. So that math-wise in my head, it makes sense because I've done it a bunch of times. And he's taking the max because it's possible that this could go out of bounds. It could go out of bounds too far to the left. And he's going to do pretty much the same thing on the right side. So a minimum of this node plus K, like how far can we go to the right, but make sure it doesn't go out of bounds. I don't know why he's subtracting this though. Oh, because he's considering the starting position of the subarray. So just to quickly look back at our example, what he's saying is we can start the subarray anywhere from here minus K minus 1. It's possible though that this could go out of bounds, so we take the max there. And then from here, we say this plus K minus 1, but that itself is not gonna be the starting position. And not only that, this part might not even exist. It could go out of bounds. So it might be possible that actually this is the furthest we can jump from here. And if that is the case, then the furthest left our window could start at is gonna be like this. So this is kind of complicated. This is very mathematical. I don't blame you if you don't understand all of it, but I'm just again trying to explain how I'm approaching this. Even the parts that I don't understand quite fully, I am trying to like bucket them and say, okay, this is the math stuff. I'm not going to focus on that too much, but this isn't super crazy for right now. Then after reversing a subarray from I to I plus K minus 1, this is like the valid range of starting positions that the subarray starts at. And then if we reverse it, the 1 will be moved to I plus K minus 1 minus node. In the end, neighbor is chosen for some interval in here. So I don't fully understand this part. Let's just quickly do it in our head. So let's say this is the starting position. This is our I, and this is the window. These are the boundaries, which he, I think, identified with some variables. In this case, it's simple. It's going to be like that. But if it were more complicated, if it were something like this, then it's going to be moving here. So what's kind of like the general formula? So I have I in the wrong position. If this was the subarray, I would actually be over here. So what he's saying is I is not always going to be in the same position as like P. And so if this is the case, then this is going to be I plus K minus 1. And if we were doing the reversal of this, P would end up over here, which is what we're trying to figure out, like where's P going to end up. So this is very mathematical. So I'm just at this point trying to verify that his formula works. He's saying I, so the left point plus the right point minus the node. node. So why is he doing that? This plus that minus this. Okay, I think I have it. I think I understand why he's doing that, because if you think about this, the distance between I and P, which in this case is 1, is going to tell us like, okay, that's 1. So then starting from here, we want to move to the left by 1, and that's going to tell us where P ends up. So that's kind of the intuition behind the formula that he's giving, I think. Not bad, but again, like this is complicated, right? Like even if you could figure this out, which I'm kind of figuring out just by looking at his solution, it's taking me a while, isn't it? Armed with this information, let's do a standard breadth first search. However, this is too slow as we are considering the same neighbors a lot. It's basically the BFS that I was talking about, kind of like, okay, you can go to these neighbors. Considering our example, we'd be able to jump here and we'd be able to jump here, but not here, at least in one jump. So this is technically a working solution. I guess that's the good thing. Like we did find a working solution, but even this one is not efficient. Okay, fine. And that's because there's repeated work, right? That's the problem. In this example, there's not a ton of repeated work, but you can imagine with this, there is a lot of repeated work. But why can't we just mark it visited? I guess that's kind of my question. I'm not sure, honestly. So let's continue reading this. To remedy this, let's keep track of which nodes haven't been reached by our BFS yet. Okay, so he is marking them kind of visited, I guess. We split these by parity into remaining of 0 and remaining of 1. Why is that? What does that even mean? When we have some interval, low plus 2 high, of potential neighbors, the reason he's incrementing by 2, I think, is just because, like, depending on the position of the array, I won't go into it, I guess, but it's the same thing, like how we could hop by 1 and then by 3, but we can't hop by 2. That's the general case. I guess that's always going to be the case. We have some interval of potential neighbors. We can query the intersection of this interval with unvisited nodes quickly, as we only consider each unvisited neighbor once. So I'm going to be completely honest with you guys. I don't understand this paragraph. I genuinely don't. I'm going to read the code to see what he ends up with. Let's see. The time complexity is n squared. And the space complexity is O of n. What is sorted list? Where did he mention sorted list? Why do we have a sorted list? I still don't understand that. Oh, I think that's the parity. That's the parity part. So I guess if we can understand why he's doing a sorted list, we can kind of understand the parity. I'm going to think about it, to be honest. I'm going to look at the code. I'm going to read it, and then I'm going to try to explain it. Okay, so I'm not gonna lie, I've been sitting here for 20 minutes now, and while I think I'm getting a little bit more of the intuition, this problem is insane. This problem is probably the hardest I've ever attempted to solve. I'm not even kidding. I can see why it is the third hardest problem on Leetcode. I think this is honestly not a Leetcode hard. I think this is a different class of problems. I think super hard. I've never done code forces, but I assume that this is kind of the caliber of problems you see on code forces. So I'm gonna keep it real with you guys. I probably theoretically could get a better understanding of this problem if I was sitting here for an hour or two, or maybe even more, just kind of whiteboarding it. Looking at this code, I can understand the high level. I can understand what he's doing here. He's partitioning half of the elements here, half the elements there. He's using these two sorted lists to mark nodes as visited. Even coming up with a solution to use one sorted list to mark them visited is very, very difficult, I think. And the fact that he partitions them into two is difficult, I think, because it doesn't actually improve the time complexity. It just improves it by a factor of 2, which usually doesn't matter for Leetcode problems, but this time it does. And just to kind of show you guys, this is a video from another Leetcode YouTuber who's better at Leetcode than me, I will admit. And you can see the contest here. Like, this was from a Leetcode contest. Only 900 people even attempted the problem. Usually I think at least 10,000 people will join each contest, but in this problem, most people did not even attempt this problem. And of the people who attempted it, only about 5% of people passed it. And these are not stupid people, just so you know. These are really, really smart people. That means probably the person who's ranked like 100 on Leetcode or 150, they were not able to solve this problem. The 150th best Leetcoder in the world was not able to do it. So, you know, look at me. I wasn't able to do it. I don't feel bad. Even to understand it, it would take me a long time. And look at this guy's video. This guy is better than me. And this video he has is 1 hour long. This guy was able to solve the problem. He was able to solve it in the contest. Let me move my camera. In this contest, he got 88 in the world. He's a very, very smart guy. You can see first question, he did it in 1 minute, 5 minutes, 7 minutes. This fourth question, it took him 58 minutes. I think the bug counts as a penalty, as a 5-minute penalty. 3. So his total finish time was 1 hour and 3. But, you know, this is hopefully, I think you at least learned like how I kind of approach problems. This one, I will admit, was too hard for me. And the reason I don't feel bad about it, the reason I don't feel bad about myself right now is because I've made a lot of LeetCode videos, 500 plus. I've solved, I think, like 700 problems. So I've probably, in terms of hours, spent between 1,000 to 2,000 hours on LeetCode. I know that sounds pretty crazy, right? And most of those hours honestly weren't like rigorous. Like it's not like I was solving problems that were challenging for me. Most of that time was spent on easy, medium questions that I was explaining on YouTube. So even that 1,000 to 2,000 hours wasn't as rigorous or as productive as it could have been for improving. I will say this guy, or the guy we talked about at the beginning, Scott Wu, these are really smart people, but they've probably spent 5,000, 10,000. I mean, Scott Wu, he's been doing competitive programming since what, he's 10 years old or something. He's probably spent 10,000 hours on this. It's true. Some people, you know, have different innate abilities, but practice goes a long way. Don't compare yourself to other people. Don't say this guy's so much better than me at this. He probably put in 10 times the work that you did. So if you put in the work, you could be better. That's not the conclusion of this video. I'm not saying you should go out and be a competitive programmer. I don't want to be. I do this stuff. 1, I enjoy it. 2, it's good for coding interviews. If I need to do an interview tomorrow, I'll probably be able to pass it. 3, I enjoy it. I enjoy making the YouTube videos. I like explaining to people. I like helping people. So that's why I do it. Don't take it too seriously. This was embarrassing for me. I'm not going to lie. I was not able to solve or understand the problem. I could probably given more time, but this time I'll take the L.